as we talk about chemical kinetics, we've been talking about reaction rates. And we said one of the things that was going to impact reaction rates were going to be things like concentrations and temperature. And one of the ways we can see the impact that these have on our reaction rates is by looking at something called a rate law. So we often describe the kinetics of a reaction using a rate law. A rate law is an expression relating the rate of a chemical reaction to concentration. It indicates the effect that the reactant concentration has on the reaction rate. So if we look at a general reaction, so we've got reactant A reacting with reactant B, producing some products. It doesn't really matter what those products are because the rate law depends on the reactants. In this equation, we've got the capital A and B representing our chemical formulas. Lowercase a and b are our coefficients. So if we were to set up our rate law, the rate law will say that my rate equals K times the concentration of reactant A raised to the power of M times the concentration of B raised to the power of N. Where in this equation, K is a constant. K is going to be referred to as our rate constant. M and N are what we refer to as orders. So notice from our balanced equation, the only thing that's appearing in that rate law are the reactant formulas. These coefficients, A and B, they do not influence that rate law. So we can look at a problem in which we set up rate laws for reactions. We should be able to take any balanced equation or any equation and write what we can call a generic rate law. And so for A, we've got hydrogen reacting with oxygen to produce water. If we set up our generic rate law, it's going to say that my rate equals K times the concentration of my first reactant raised to some power times the concentration of my second reactant raised to some power. Now, in an actual rate law, we would actually have numbers for those M and N values. But right now, we're just getting the general format. So it's K times the concentration of each reactant raised to some power. Now with B, we've got 3 reactants. It doesn't change the way we set it up. The rate equals K times the concentration of X to the power of M times Y to the power of N times Z to the power of O. So here we're just setting up the general form. We'll talk a little bit later about how we actually determine what these M and N values are. Now, before we do that, we need to know what we mean by reaction order. So we represent that with some variable M, N, O, depends on how many reactants we have. What this reaction order does is it determines how my rate depends on the reactant concentration. Now, these values are usually, not always, usually small integers. And we come across 3 common orders. We've got 0, first, or second order. So 0 is where our N or M value equals 0. What this means in terms of our reaction is that the rate is independent of the reactant concentration. So I can change that particular reactant concentration and it will not change my rate. Now, a first order is when our N or M is 1. What this means is that my rate is directly proportional to the reactant concentration. So whatever I do to the reactant, the same thing occurs to the rate. So if I double the reactant concentration, we're going to see that our rate doubles. And then finally, for second order, that means our N or M value is equal to 2. This means that the reaction rate is proportional to the concentration squared. So if we double the reactant concentration, we're going to find that the rate quadruples. Now we have multiple reactants typically in a reaction, and so we can also refer to an overall reaction order. This is the sum of the orders on each reactant. So for example, if we've got the equation that says that rate equals K times the concentration of A squared times the concentration of B to the power of 1 times the concentration of C to the power of 0. That particular reaction would be described as being second order with respect to reactant A, first order with respect to reactant B, zero order with respect to reactant C. Now the overall order would be the sum of those orders. So 2 plus 1 plus 0 gives us an overall third order for our reaction. So how do these impact our rate? And so when we look at how they impact rate, we want to look at each reactant individually and consider the following changes. So if we talk about the reaction being second order with respect to reactant A, that means if we double A's concentration, we raise it to the power of 2. So this is my concentration change raised to my order. 2 squared is going to give us 4. So this is how my rate changes. So that's why we say it's proportional to the concentration squared. If I were to triple my concentration, so we would have 3 squared, which would make my rate 9 times faster. And so again, the way my rate changes is proportional to the concentration squared if it's second order. Now for my first order, so if we look at B, if I were to double B's concentration, its order is 1. 2 to the 1 would be 2. So if I double my concentration, my rate doubles. So they are directly proportional. Same thing if I were to cut my concentration in half, then my rate would cut in half. And then finally, for zero order, if I were to double my concentration, we raise that to the power of 0, that's going to equal 1. So anything raised to the 0 order equals 1. So I could double my concentration, but my rate is only 1 times as fast, which means the rate doesn't change. So we're going to use these relationships in order to identify the orders for our rate laws. So if we look at this example, we've got the reaction of A with 4B producing products. We want to determine the rate law for this reaction. We see that when A is doubled, the rate is 8 times faster. So we would have done this or figured this out by experiment. We would have gone into the lab, we would have doubled A's concentration, and we would have seen how the rate changed. When B was tripled, we found that the rate was 1/3 slower. So in order to determine our orders, we're going to start by writing our generic rate law. So that's going to say that rate equals K times the concentration of reactant A raised to some order times reactant B raised to some order. Now the next thing we need to do is determine the values for our orders. So the way we would do this, if we want to look at M is the order on reactant A. So we look at how changing A's concentration changed the rate. So A was doubled. So I'm going to take the factor by which my concentration changed. I'm going to raise it to my order, and I'm going to set it equal to my rate change. We said the rate was 8 times faster. Now at this point, some of you may be able to look at this and tell right away what that value might be. If not, you're going to have to solve for your M value. And the way we solve for exponents is using logs. So we're going to use the log rule that the log of a to the x equals x times the log of A. So that's going to allow us to get that power out of that location. So we're going to take the log of both sides. We're going to do the log of 2 to the m equals the log of 8. So rearranging using that log rule, we'll get m times the log of 2 equals the log of 8. So m is the log of 8 divided by the log of 2, which is 3. So that now tells me my order with respect to reactant A. My reaction is third order with respect to reactant A. Now we need to solve for our N value. So we're going to do the same thing. We're going to look at B because N is the order on B. We're going to see how we changed B's concentration. And B's concentration was tripled. We're going to raise it to our order of N, and we're going to set it equal to the rate change. The rate was 1/3 slower. So again, you may be able to look at this and recognize that that N should be -1, since something raised to the -1 is 1 over that value. But if you don't recognize that, you're going to solve using your logs. So log of 2 to the N equals the log of 1/3. N times the log of 2 equals the log of 1/3. So my N is the log of 1/3 divided by the log of 2, which gives me -1. So my rate law will say that my rate equals K times the concentration of reactant A raised to the power of 3 times reactant B to the -1. So this is third order with respect to reactant A. It's -1 order with respect to reactant B. My overall order would be the 3 plus the -1, which would be overall second order. So with problem number 2, we'd be doing the exact same thing that we just did with our example. We're going to write our generic rate law, which will say that my rate equals K times concentration of A raised to the M times B to the M. We're determining M, so that's the order on A. We're looking at how A changes. So A's concentration doubled. Its rate was 16 times faster. We would solve using our logs. And so we would get that our M value is 4. For B, to determine N, B doubles. The rate became 1/2. So that means my N value is -1. So my rate law here says my rate equals K times the concentration of A to the 4 times B to the -1. So here we're just looking in general at how doubling or tripling or cutting things in half, how they're going to impact that rate, and then we're using that to identify the rate law. Now this whole doubling and how fast the rate gets, this is all determined from experiment. So M and N are the orders in our rate law. Now we've got another component of that rate law, which is K. K is our rate constant. K is described as being a characteristic of the reaction, which means it depends on the specific reaction itself. So it's different for every reaction, and it depends on temperature. Our units are going to vary depending on our overall order. So it's going to be very important that we watch our units. So if we look at an example, our rate say we have the following rate law. Rate equals K times the concentration of A squared. Where our units, or determine our units, we know that rate, we're typically looking at molarity per second. My concentration's in molarity. So if I plug those in, so I'm plugging in the molarity per second for rate, I'm plugging in molarity for my concentration. And we're just rearranging these. So we're treating those units just like numbers. We're rearranging and we're going to solve for K. So to rearrange and solve for K, I'm going to need to get K by itself. So I'm going to divide both sides by m squared. So they end up with molarity divided by seconds times molarity squared. Molarity on top and one of the molarities on bottom cancel. So that leaves me with 1 over seconds times molarity. Or we can write that as seconds to the minus 1 times molarity to the minus 1. So that was if our rate law was second order. Now, say my rate law is first order. I do the same thing. I plug my units into my rate law. So molarity per second for the rate, molarity for the concentration. I rearrange to solve for K. So I'm dividing both sides by molarity. I end up with molarity divided by seconds times molarity. Molarity on top, molarity on bottom cancels. So in this case, my units are just seconds to the minus 1. So here, it's going to be very important to keep track of your units. We can't just assume we have one set unit for K because it varies depending on our rate laws. And so with problem 3, we've got some more additional practice. For problem 3, if we were to plug in our units and rearrange this, and again, I would encourage you guys to practice these. So these are something you would have been doing in your worksheet. You should have practiced these in class. If you're doing these at home, you should practice them first before looking at these answers. But my K would end up being 1 over seconds times molarity squared. For B, now we've got 2 reactants here. It doesn't really change the way we do things. We're going to have molarity squared for A, molarity squared for B. So molarity squared times molarity squared is going to give me molarity to the power of 4. Rearranging, I've got molarity over seconds times molarity to the 4. Reducing, I get 1 over seconds times molarity cubed. So again, our units are going to vary. So we've looked at rate laws in general, writing a generic rate law, determining orders from information such as did something double, how did the rate change, and looking at units of K. In our next video, we're going to take a closer look at how we take experimental information and use that to determine our rate laws.